orientation and enough energy. Okay. So activation energy, so this you already know, right? So this activation energy is due to this energy barrier, right? So you have to overcome this energy barrier to have a reaction. So that activation energy is the energy barrier you are looking at, and that you already know. I'm not going to discuss that. Now, how to measure the reaction rate? So reaction rate, it's about the product, right? So you are going to measure in the product side the volume involved or the mass involved, increasing or decreasing mass. Then if it is a experiment where the color is involving color change, then if it is a reaction which includes precipitation, you measure that. If it includes acid or base, so that, and then the change in temperature. So these are the uh, factors that you will observe. So these all are you observe, measuring reaction rates. Observe, right? So here you have delta H value, right? So you're looking at delta H value here. Yeah. Right. So if you look into this one, time versus concentration is plotted, right? So reaction using the concentration of H2 plotted against time here. So now, if you look into the dotted line, dash line, represent another way of progressing this reaction. This is another pathway. This is another pathway. Right? So you can see the gradient here. You can see the gradient here is more than the before. So that means rate is high here. Rate is high here. So how do you know the rate is high? Because you need this H2 concentration, how that is changing with time. So that is the rate in this case. Okay, so that rate is high for the new pathway. Okay, so that's what we are discussing here, right? So you can read it, right? Now, we have to understand open closed systems. What is a system? So system is something you consider, or in this case, reaction under consideration. So that's the system. Surrounding everything else. So outside the system. Outside the system. What is an open system? Open system, both matter and energy between the system and surround. So it allows to transfer or penetrate matter and energy both. Matter and energy both. So that's an open system. If it is a closed system, matter you cannot uh, transfer, but the energy will transfer. Energy can be transferred. So this is important. Closed system, matter can't be transferred. Not allowed. Not allowed. Isolated system, so matter and energy both cannot be transferred. Okay, so that is easy. Okay, so I'm explaining the surrounding and the system and energy, matter, closed system, open system in this diagram. So you can just read through that. It's easy thing. Now here you have an open system and you have a closed system in this case. So what we are doing is So we have ethanol here, and then you let ethanol to evaporate, and then it's open system. Open system means particles can go out and energy can go out, not just out, both ways. So in here, energy can go out in, energy can go out in, but the particles can't go because of this barrier, right? So what will happen? So these particles are trying to move up, and then once it hits this surface, they are going to come back and then settle in here. So it comes to an equilibrium situation. So what do you mean by equilibrium situation? So this is equilibrium situation. So what do you mean by equilibrium situation? Here you have ethanol, I would say C2H5OH, liquid is what you have here. And here you have C2H5OH gas. So equilibrium situation means C2H5OH liquid. So you do this C2H5OH gas. So gas becomes liquid, liquid becomes gas, right? So in this situation, no equilibrium at all. No equilibrium at all. So all the ethanol will be evaporated. Okay. So that is what we are discussing here. And this is what the equilibrium situation we discussed. Okay. So you can read through that. So that's this already I discussed. Okay. What actually happens in the closed system? So gas molecules collide with each other and the wall of the flask. Okay, that is the first thing. Gas, important. Then they collide with the liquid surface and reabsorb. So what will happen? The gas molecules bounce back and absorb in the liquid surface and then reabsorbed. So reabsorption means this is the liquid surface. So these particles are coming in and then absorbed. Actually, those particles were emitted and then coming back and absorbed. The amount of gas molecules evaporating, higher the chance of reabsorption. So there is a higher chance of reabsorption because it's a closed system. This is closed. This gate is closed. Okay, that is easy to understand. So at some point, the rate of evaporation and the rate of reabsorption will reach an equilibrium. So that we already discussed. So that means coming in and going out is going to be the same, and that is called equilibrium. So then there is no overall change in mass or gas pressure at the equilibrium. So there is no overall change in mass or gas pressure at the equilibrium. Okay. So that is when the system is at equilibrium. So now, in a closed system, when the particles are moving out, what about the pressure here? Pressure initially increasing. Pressure initially increasing and decreasing with time due to this reabsorption by the surface. Okay, easy things. Right. Now, factors affecting the rate of chemical reaction. So there are 5 which we already discussed, and then now we are going to go through that individually. Concentration, gas pressure, temperature, surface area, presence of catalyst. So all of these things are tested in the exam. Will be tested in the exam. Okay. Okay, so first of all, I want you to read this concentration part, and then it's easy for me to go through. Calculate this concentration part for me. Okay, so concentration. Now, if you look into this one, right? So H2 plus NO H2O and N2. So all of these are gases, right? Uh, yeah. Okay, Kavya, tell me what would be the molar volume of a gas? Molar volume of a gas. How much that? 24.8 liters per mole. Hmm? At yeah, correct. At SLC. At SLC, right? Yeah. So why it is not important here, but all of these are gases, right? So here, so when we are dealing with those numbers here, you can do that in the future. Okay, anyway. So if you look into this experiment, what we are doing here, in the first two experiments, this part is constant. The first two experiments, this part is constant, but you are changing the H2 concentration here. So when you increase the H2 concentration, you can see the rate of H2O production rate has increased, right? So again, when you look at the third and the fourth one, uh, sorry, other way around. So third and the fourth one, H2 concentration is the same, but you are increasing the NO concentration like this. So when you increase the NO concentration, you can see in the right hand side, H2O concentration also increased, right? So what happened when you come here, when you increase this one by keeping this constant, that means this H2O production increases. That's what we see, right? So it tells you that concentration is a factor. Okay. So that is what we are explaining here. So whatever I explained here, it's written here. So now you go to this part. How can increasing the concentration result in increasing the rate of reaction? So this process you have to write in the exam. Increasing the concentration of one or more reactants leads to more particles in a given volume. So leads to more particles in a given volume. So higher the number of collisions. So more particles means higher the number of collisions. Higher the number of collisions. Then higher the number of collisions, there are higher frequency or there are higher number of successful collisions. So every collision is not a successful collision, right? So, but you get higher number of successful collisions. So successful collisions increase the rate of reaction. So then you have to understand it's all about successful collisions increasing the rate of reaction. Successful collisions. You get it? So that's the whole point. So you have to understand these steps. Okay. Yeah. Say again. Collision means mobility. I don't know what you wrote, but mobility is like mobility is mobility is ability to move, right? So ability to move a particle, right? So if ability to move a particle is more, that means more collision. Maybe that you wrote in your language. Maybe. Mhm. Don't quote me something you wrote. But I think that's the idea. Yeah. So gas pressure. Um, so increasing gas pressure is an increase in rate of reaction. Okay, let's see what will happen when you increase the gas pressure. So when you increase the gas pressure, decrease the volume. Tell me why. Jansen, tell me why. Increasing gas pressure, why decreasing volume? Why I'm saying that? Why that makes sense to you? Why that makes sense to you? Increasing gas pressure, decrease in the volume. Why that makes sense to you? Increasing gas pressure means more particle. Why? Yes, Arvind. So give me some chemistry overview. Uh, Give me some chemistry overview. Okay, look at this. Look at this. So you guys know PV equals to nRT. N is a constant, R is a constant, if T is a constant. If T is a constant, what is T? If time is a constant, right? Right, Tishani? If N and R and time is a constant, right? Yeah, yeah. Can someone give a slap? PV is equal to nRT. T is time. T is temperature. I'm saying N and R constant, and if temperature is constant. Huh? I said time, but she said yes. I repeated that. N is R and time, and she said yes. Why are you confused? Right. So PV, so then PV is equal to K. K is constant, right? PV is equal to K is what, Jansen? What is that? PV is equal to K means what? What? Is it something you know? PV is equal to K is Boyle's law. You don't know that? Why you don't know that? I discussed it. Okay, fine. So this is Boyle's law. So when pressure is increasing, according to that, volume should decrease. Why? Because right-hand side is a constant. So that's why. Okay, quick catch up. PV is equal to nRT. What is that equation, Nimesha? We call it gas equation. Okay, listen to me, Josh. N is called number of moles, R is called gas constant, T is called temperature. Sometimes people use delta T, temperature change, but it is temperature. P is pressure, V is volume. All are coming in SI units, right? Now, you discussed this in 3 different branches. I already discussed that. I'm going to revise. First one, PV divided by T is equal to NR. Next one, PV is equal to nRT, and this side is a constant. So here this one is a constant. Third one, V divided by T is equal to NR divided by P, and this one is a constant. So what I'm saying, you consider N and R to be constant in one side. In another one, nRT divided by nRT becomes a constant. The other one, nR divided by P are considered to be constant. So in that case, you can see from here, this is going to be V divided by T is a constant. So in here, you can see PV is a constant. PV is a constant, right? So those are special case of PV is equal to nRT when you consider T is constant or P is constant, right? So this is called Boyle law. Boyle. I think BOY, I think. Boyle's, I think. Scientist, okay, I forgot the name. I forgot the I forgot how to write the name, but it's Boyle's law. Is it right? Okay, Boyle's law. The other one is called Charles law. Charge law. So what we used here, Josh, we use Boyle's law here, thinking N, R, T are constant, so PV is equal to K. We use the Boyle's law in this to understand why it is happening. It's okay. So now, increasing gas pressure decreases the volume, right? So you understand that from this background. More particles in a given volume. So if volume is decreasing, that means everything is compact. So more particles in a given volume. So particles are concentrated. So more particles means higher the number of collisions. Then higher frequency of success collision, increase the rate of reaction. So you have to understand, no matter what, are you listening? You have to understand, no matter what, if you want to have increase of the rate reaction, you have to have successful collisions. So whatever the logic you are bringing in should be leading to this successful collision theory. Okay. So if you look into the previous one also, you can see successful collisions and increase in the rate. Whatever the theory, whatever the logic you are building here, ultimately should lead to successful collisions. Uh, yeah, correct. Temperature. Now again, if you look at the pattern, increase the rate of reaction here, and that's due to number of successful collisions. So now, logic behind it. If you increase the temperature, obviously the particle have more kinetic energy. If the particle have more kinetic energy means they move faster. So if they move faster means they collide more, right? So that is what I'm showing you here as well. Okay. Read this one. I will explain after. Read this one quickly, everybody. Let's work now. What is Boltzmann distribution? Boltzmann distribution. Okay. Maxwell-Boltzmann distribution, this distribution mostly coming in chemical physics. Chemical physics. If you do physics also in year 11, you have this Boltzmann distribution, Maxwell-Boltzmann distribution. So Maxwell-Boltzmann distribution is nothing but how the number of particles, how you plot number of particles against kinetic energy, right? So that has a shape like this. This is not a perfect bell curve. Now you have to understand, my friend, right? Look at this. This is T1 temperature. This is T1 temperature. Now that means at T1 temperature, how the particles are behaving, right? So now you have to understand, for example, you have A plus B goes to C plus D, right? And this is happening at T1 temperature, right? At T1 temperature, to get this business done, you have an energy barrier which is called activation energy, right? So that activation energy, because your x-axis is energy, so this is your activation energy. Right? So whatever here, only participate to the reaction. Only participate to the reaction. Do you agree with me? They only participate to the reaction. Okay? So what about the rest? Rest is not. Now, Boltzmann distribution shows you if you increase the temperature, this distribution shift to right like this. And that is T2 temperature. Obviously, T2 temperature is greater than T1 temperature. That's the whole point. Now, what will happen? If you increase the temperature, nothing will happen to the activation energy. Right? But what will happen? You can see extra amount of particles are coming into the reaction. See? Extra amount of particles are coming into the reaction. So that means the reaction rate is increasing. So that is what I'm explaining here. And everything is explained. So that's it. Okay. So remember Maxwell-Boltzmann distribution. Okay. Okay. So things are explained. So just read it the same thing what I explained to you. Okay. Let's go to the surface area. So now when you increase the surface area, when you are increasing the surface area, the reactant particles are exposed. More reactant particles are exposed. So that means higher number of collisions. Again, the same story, higher number of collisions. So more successful collisions and then increase the rate. Okay. So that's it. Give me example. Give me example about the surface area. Give me example. Yes. How that surface thing? Oh, you are talking about the fuel cell? Ah, yeah. So he's talking about the fuel cell. So the membrane you are talking about, right? So if you have the membrane and then you provide the surface area, high, big surface area, so then the the reaction rate is high. Exactly. There is another everyday example. The other example is this. You know sugar. You know sugar. Why sugar particles are this thick, this small? Sugar can be like this kind of a big particle, like a big one, like a stone. Why? Because it wouldn't dissolve quickly. So sugar, small particles, high surface area, high surface area. That's why surface area is a big thing. Okay. Anyway, okay. Read this one. Some extra knowledge here. Combustion reactions are also affected by surface area. When the surface area is high, combustion occurs rapidly, sometimes causing explosions. Coal and wheat dust have a higher surface area and leads to explosive combustion. Okay, so surface area is that. Good. So, okay, can we try 4.012? Yeah, 4.0 through 03. Guys, can we try these three questions quickly? Hello, don't waste time. Then I will discuss. Okay. The gaseous reaction was carried out in four different systems. Okay, as follows. In which system is the rate of reaction faster and why? Which one? Hmm? Which one? Which one? C. Why? Yeah, answer is C. Highest temperature and pressure. So then the pressure is high means more collision. Temperature high means again more collision. Right? Yeah. So that I don't have to explain. In which system is the rate of reaction is lowest? B. Okay. In the reaction between sucrose and concentrated sulfuric acid. What is sucrose? What is the equation? Chemical? How much? C12? Glucose, right? No. C12, H22O, that's sucrose. Concentrated sulfuric acid. Sulfuric means H2SO4, yeah, H2SO4. Concentration, concentrated, concentrated. Um, what do you mean by concentrated sulfuric acid, Atreya? Concentrated sulfuric acid means what? What do you mean by concentrated? Mm. What do you mean by concentrated? Concentrated sulfuric, diluted sulfuric. What is the difference between? Eh? pH. So diluted H2SO4 is pH is less and then the concentration is high. Is that what you think? Yeah, what is the difference between concentrated and dilute? You put into water, right? Okay, so what is the difference when you put into water versus you don't put into water? What is the difference? Yeah, but that's the whole point when you mix it. But what about, so here, this is like H plus and SO4 2 minus, right? H plus and H2O4 2 minus, right? So what will happen to H plus? What do you mean by H plus? Uh, okay, concentrated means this H plus is released very quickly, very quickly. In the diluted version also H plus is released, but slowly. So it's not about H plus, it's not about H plus concentration. It is about rate of H plus concentration is high in the concentration. Rate of H plus concentration is high. Rate of H plus concentration, not H plus concentration. It's the same for diluted version as well. What do you mean by rate of H plus? How many H pluses are coming in a given time? Right? In the concentrated version, it's more. Okay, anyway. Explain why the caster sugar has a higher rate of reaction than granulated sugar. Okay. Okay. Explain. So you know the caster sugar is very small particles, and the granulated is little bigger. So the surface area is the factor here, and so caster sugar has higher surface area. So surface area is high means the reaction rates are high. Therefore, you know, uh, yeah. So the caster sugar has a higher reaction rate, right? Castor is high surface area, then granulated low surface area, high surface area, low surface area. Okay. Okay. What about this one? So you have this, if this reaction occurred in a constant volume system, okay. Explain why the rate of reaction decreases with time. Further explain if the progress of the reaction can be monitored by measuring the change in pressure. Okay. What is the answer for this one? For Purnara? What? Okay, so you have to add. Okay, read the question. You have to address constant volume, right? So what will happen in the constant volume? Explain why. Why are you addressing why? why the rate of reaction decreases with time. Why? Further. Explain the if the progress of the reaction can be monitored by measuring the change in pressure. Say it again. Okay, finish. P is proportional to N. So the number of moles of reactants is directly proportional to pressure. Then when the reaction progresses, pressure. Okay, Arvind, what is the answer? Huh? Say it again. Reactants are used. Used to, what do you mean by used for products? Reactants. So that means it is reacting. Okay, look at this. Can you see one here? Can you see one here? Can you see, if you look into the left-hand side, how many moles are there total? Right-hand side? So that means number of moles are reducing. If the number of moles are reducing, that means number of particles are reducing. So that means constant volume. So this volume. Initially you have 10 particles. Now you have 7 particles. When you have 7 particles, what will happen? Pressure decreases. Pressure decreases. So that's what it says. So explain why the rate of reaction decreases. So you have to say when volume is constant, the number of particles are going to be less in the product side. So then eventually the number of particles are going to be less. Hence the pressure decreases. So pressure decreases, reaction rate decreases. You understand? So this observation is a very important thing in the future as well. So you are looking at the number of moles to determine the pressure. It's true, ne? Moles are less means pressure less, right? So that's it. Okay, so you can just write that. Okay, I don't need to write. Yeah, you can write it. That idea, right? Right. Now, surface area, volume, pressure, temperature, those things are done, right? Last part, catalyst. Please read through this page and then I will take over quickly. Okay. Hasini, what is a catalyst? In the reaction. Okay. So, okay, you know what is a catalyst. What are the benefits using catalyst? I think you read it. Facilitating reactions to occur at low temperature and pressure, because you have to understand at low temperature and pressure, reaction rate is low. Low pressure and low temperature, reaction rate is low. So you introduce a catalyst to get that done, right? Okay. So, and low energy consumption, providing environmental and economical advantages. Okay, so that we can discuss. Now, let me see whether I have that picture. Yeah, okay. That I will discuss that in a minute. So, what catalysts are doing, they are finding alternative pathways. What they're doing? They are doing alternative pathways. Alternative pathway means when the catalyst is introduced, so it will be like this. It will go to that easily, like maybe here to this level. So this one is coming to this level. So it's a new pathway. New pathway. So catalyst will give you new pathways. Now, are we changing temperatures? Okay, look at this. Now think about Maxwell-Boltzmann distribution, okay? So think about Maxwell-Boltzmann distribution. So when you have this becomes this when you increase the temperature. When you increase the temperature. Now that we understood. So think about you are introducing a catalyst. What will happen? When you introduce a catalyst, this will happen. Temperature T1 became the same because we are not touching the temperature. This is your previous activation energy. This is your previous activation energy. What will happen? You are going to shift the activation energy to left. So you are going to move the activation energy to left. So what will happen? The number of particles are going to be number of particles are going to be high. Correct? So that means the rate of reaction is high, right? So now we discussed that this can be done in low temperatures. So suppose this temperature is very low, and then only this much is participating to the reaction, and the reaction rate is very low. So you can increase that the number of particles coming into the reaction by shifting this activation energy. How to shift activation energy? Using a catalyst. Okay. So that is what I'm explaining here. That is what I'm explaining here. Right. So I'm not going to discuss this, but I will go into here this question. Okay. Try this question quickly, guys. Guys, very soon we are going into the past papers. So then, yes, I'm going to finish it very soon. Rate of reaction and equilibrium. Not today. By next week, everything is done. Le Chatterley's and everything will be done by next week. No, unit 3, all done. So then I can give you unit 3 past paper questions to do. So that's the place where we start past papers. We have, I forgot, we have the class on Monday, 2:30. Yeah, I said that, right? Monday, 2:30, class is here. 2:30 to 5:30. I'll discuss that. Face to face. Huh? So let's try to arrange something. No, it's just here. Why online? So then I can easily do it online, but I can't do that. So because probably Monday, and then next Saturday, in equilibrium and everything is done. So next Saturday, we are officially moving into past papers. Huh? Unit 3. Unit 3 has past papers. And then unit 4 is going to be an easy game. Spectroscopy, I need to start. Spectroscopy is a physics concept. Then organic chemistry, which is a very easy thing, which I have already done, and then I'm going to redo it. And then that medicinal. Medicinal thing is is a easy piece, theory wise. Then I have to see how you guys are writing your, descriptive questions. By calculation questions should be all right with the proper practices. But you have to remember, depending on your school, your sax might scales down. And Kavya, you have to be very careful, ducks in your school, right, Kavya? Ducks in your school, he got A pluses for sax, and then all those A pluses became B plus when it is coming to the final. And he got A plus for the final paper. He got A plus for the final paper, so they can't touch that because that's the final raw result, right? But his A plus, SAC result became B plus when it comes to the result sheet. It's because of your school. Don't ask me that. I don't know why. It's because of your school. Huh? 40 something, 42 or something. So he was number one. He was ducks in his school, KC Grammar, yeah? KC Grammar, and he was the subject winner as well. He was the subject winner as well. And that happened to his specialist math as well. Scale down. He got 50, but I saw the result, he scaled down. SAC scales down. So he got 50, it's a scale, but he deserved maybe 52, 53. Scale down. I can see that from the thing. So it depends on your school. And if he is in Melbourne High, it wouldn't happen. Nosal, it wouldn't happen. Right? Can't help. Revenus is ducks in your school, right? Yeah. Revenues, the same thing happened? Revenues specialist math 50. Revenues math method scale 50. Revenues math method scale 50. So revenue got 45, 46 row for methods. 46 row. But he got 46 row with a perfect accuracy. If revenue was in nozzle, that would be row 48 or 49. Yeah. I can't say that because I saw A plus in his sack, but I feel like he got little below because A plus is a range. So his 99 A plus became maybe 90 A plus. I can't say revenue because revenue's sack is like almost 100%. So I can't see. He got A plus, but can be a low 90 A plus. Scale down. Yeah. But you have to be very careful with non-scaling subjects like physics. Chemistry is by 4, but it depends on the cohort as well. Because the cohort is not performing, it's not performing. Yeah. Okay, this one. This reaction has an activation energy 350. Delta H is given to you. If the catalyst is used, okay. This question goes to Shamita. Delta H is positive means what? Huh? Huh? What? Question is delta H positive 1000 kg means what? Endothermic or exothermic? Endothermic? Are you sure? Endothermic. Okay, so show all the information on the energy profile diagram. Okay. Okay, how do you do that? Do you do that? Okay, so it's endothermic, right? So endothermic should be here, like it goes like this and this. So 350 is going to be from here to here. 350. Okay. Then activation energy is fine. So then this length would be, this height would be 100. Okay. Then if the catalyst used, the activation energy is 120. So, 120 is like this. So that means this height is 120. That's it, I think. Yeah. Calculate the activation energy for the uncatalyzed version of the reverse reaction. Uh-huh. Okay. What about the reverse reaction, guys? Huh? Calculate the activation energy for the uncatalyzed version. So that means that the red color one. So that means you are going from, you are looking at this side, ne? You are looking at this side. Agree, everybody? So that's going to be 250. So it's going to be 250. I have a question, Shamita. Enthalpy can be positive, negative. Ne? Enthalpy is energy, right? Energy kind, right? Type of, right? So energy. So that can be positive, negative, right? Activation energy, can that be positive and negative? Enthalpy is an energy, positive, negative, endothermic, exothermic. That's fine. Activation energy, can that be positive, negative, relating to enthalpy? Hmm? Yeah. On why? Hmm? Always positive? Why? It doesn't matter you are going front or back, like means reverse process or the forward process. That energy should be provided to break the bonds. So bond breaking energy is finite, cannot be negative. So you have to always provide. That's what I'm saying. You can't take it out. You provide all the time. Okay. So how do catalysts work? How do catalysts work? So that we already discussed here, right? So I'm not going to discuss that anymore. Okay, read this plot. Some misunderstandings, I try to put it here. Catalysts do not lower the activation energy of the existing reaction pathway. Why is the first? Okay, read the question. Catalysts do not lower the activation energy existing reaction path. Oh, it's a different pathway. Yeah. Yeah, English is tripping, yes. Existing. So it is not existing, it's a new pathway. It's a new pathway. Also, catalyst increase the rate of reaction, not by increasing the energy of the reactant molecules, but providing an alternative pathway. Yes. So catalysts are not increasing the energy of the reactant molecules, but providing alternative pathway. Yeah, this misunderstanding, right? Some people think catalyst is provided, so energy is go. Energy wouldn't go up. Okay. You know what about it? You know about enzymes. It's a natural biological catalyst, right? Right. So that's fine. So, so catalysts we find in many industrial processes aligning with green chemistry principles. Industries are heavily relying on catalysts as they contribute to significant decrease in energy consumption and thereby providing economic benefits. So, in the future, I'm going to give you similar questions to answer using green chemistry principles. And when you use catalyst, explain how that can be used, how that can be explained using green chemistry principle. Uh, and according to this, significantly we reduce the energy. If catalysts are not there, we need to provide energy to bring the particles to move. You understand what I'm saying? So you have to increase the temperature. You are increasing the temperature means you are providing energy. So you are providing energy means cost, right? A lot of issues are there. So you introduce a catalyst. So then we will write down those things properly from next week onwards. So industrial reactions must be taken place at very high temperature to be successful. Providing energy to raise the temperature will be costly. We discussed that. And high energy consumption. But the same result can be obtained by normal temperature by using catalyst. That is what we discussed already. Okay, answer this question carefully. Yeah. So catalysts provide an alternative pathway with a lower activation energy. So, so uh, more reactant. What is the problem? What is the problem? More reactant molecules, more reactant molecules have enough energy. So more reactant molecules have enough energy to overcome the uh, energy barrier. Energy barrier. So this leads to, again, this leads to more successful collisions. This leads to more successful collisions. Successful collision. Hence, faster reaction rates. Simple, super simple, right? Yeah. Okay, so this we already discussed. So just read this one. These are like pretty, some extra things. You don't really need that. So questions are starting from here, right? So these questions you have to do for homework. And all the past paper questions you have to do until this by Monday. By Monday. This Monday. What do you mean by what is that question? 2 days? Yeah, 2 days means like 48 hours. Huh? Monday morning you have, Sunday night you have, tonight you have. You have this, so you can use your. That's fine there. That's fine. You don't have styles? That's fine. So once you're done, push yourself to do it. So when you're done by Monday, I'm going to start this equilibrium. So This will have some math calculations, but not a big deal. Not a big deal. Okay. So that's it.